Grant, structure of the superconducting phase in above 90 Kelvin yttrium compounds.
You'll have to give me a second to wire myself up here so I don't catch it in my beard. Here, get this. Well, thank you all for waiting. I know it's late, and I hope to make this talk worth your wait. First of all, I have to show you a foil with some names of people who have worked very, very hard in the last 2 months. These are the happy band of high TC warriors at IBM Almaden. And we began working in this field in early January when most of us couldn't even spell perovskite. I want to spend a minute or so just running through the people and what they did. The synthesis team was led by Ed Engler, and with help from Victor Lee and Ed Nazal, they have made well over 200 samples in the last 4 weeks. The characterization was done by Robbie Byers, Tom Shaw from Yorktown, who we've made an honorary member of Almaden for the past week or so, Grace Lim, and Rick Savoy. Robbie is the guy who did all the beautiful TEM work that I'll show you, and was the one who told us the direct route from a microprobe and TEM analysis of the original CHU starting material. Saved us a lot of matrix evaluation work. And he showed us how to separate out the green phase, and that's how we found out that the green phase was really a red herring. Measurements, Stuart Parkin did magnetometry, Jamie Kaufman helped in transport, Michael Ramirez, Jose Vasquez, and occasionally I even went into the lab. And on theory, we had a good deal of help and encouragement from Frank Herman, who kept us from getting too wild. Now what I'm going to show you, it just doesn't do justice to Robbie's pictures. And he's here, and I urge you to try and get a hold of him so you can see what the photographs really look like. But these are really beautiful pictures and a tour de force in microscopy. Here is a picture of a single crystallite of 1, 2, 3. By the way, at the end of this story, we're going to agree pretty much with the Bell crystallography. The only thing that we won't agree with is the way they count. We like to call this 1, 2, 3. For some reason, they want to call it 2, 1, 3. But that's really going to be our only disagreement. Here we're on a 12 angstrom scale. Clearly you see the barium, yttrium, barium ordering. Convergent beam definitely shows the loss of a Muir plane. The space group is PMM2. We have put the cell horizontally in conjunction with standard crystallographic notation of having the C-axis along the two-fold axis. So there's some small distortion in this direction of the yttrium and the barium. How much, we don't know. The other thing to notice on this micrograph is this large white space in here. And our beginning thoughts were that these were oxygen vacancies in the copper basal plane, and you see here we've marked possible candidates. We really can't say anything about the oxygen vacancies in the yttrium plane. They could or could not be there according to these data. If they are there, I'm still a little concerned about how yttrium 3+ would collect enough negative charge to satisfy its valence. Perhaps it's not yttrium 3+, perhaps it's some other valence, and that should spur on some core level spectroscopy on yttrium. Okay, what we now see from Bob Haven's nice results that this could possibly be a reconstruction going on in the copper basal plane, opening up these white space where the electron beam just pours right through, and that what we're seeing are the copper vacancies along this line, and then a spreading of the space between the barium atoms due to this reconstruction caused by oxygens in the barium plane moving toward the copper. And I think the story is beginning to look very, very pretty in that regard. Okay, just to show that we do superconductivity, here's a foil where, I don't know how well, it shows all right. Same sample, but annealed at different rates out of the furnace. This is fast cooling out of the furnace. This is slow cooled out of the furnace. You get two entirely different responses. Very percolative superconductivity for the fast annealed sample. Obviously, you're not getting oxygen equilibration. Slow cooled, it's very, very narrow. Was that the 5-minute bell?
It was.
Okay. I just have to show that we too have done one more foil. We have done a series of runs of substitutions. These are the ones that work. These are the ones that don't work. These are the large elements in the lanthanide series. We also have done alkaline earth substitutions. I don't remember seeing any of this tonight. I think this is a new result even this late in the evening. Thank you very much.
Thank you, Dr. Grant. The